Oops. All right, polar graphs and calculus. This is what, 10.3 through 10.5. Okay. So we're going to do some of the stuff in 10.3 through 10.5. So 10.3 is just about what is the polar graphing system. 10.4 is what are polar functions, and 10.5 is polar calculus. So what's the idea of polar graphing is pretty easy. You're gonna, if you haven't done it before, you'll pick it up pretty quick. Polar functions take a little more getting used to. We're gonna need another class or so to play with those. And then polar calculus also takes a little getting used to. So my favorite analogy for polar graphs is kind of like a radar scope. This signal broadcaster spins around, sending out radar, and it bounces off things and then comes back. And so what's recorded when something is pinged, like say something right here, when that information goes out and back, is the angle that was measured from some reference line. And our reference line, just like in basic trigonometry, is the positive x-axis.
Should I be drawing this in different colors?
Whatever floats your boat. Yeah. So the positive x-axis is my reference line, right? Yes, that was a yes. That was a yes.
So we should be drawing
Sure. Yeah. Or you could just watch this part.
are we going to be graphing on this later?
You're going to be graphing on that later, so you might as well just watch this part. Yeah, just watch. Okay. All right, how many grid points do I have on here? I have 1, 2, 3, 4, 5, 6, 7. I have 8 concentric circles. Let's say the radius of the first circle is 1, so that means this guy right here is 8 units out, that x. And if you kind of focus on the lines here, there are some major lines drawn here, and then there are some minor ones in between. And the major ones look to me that this angle right here is pi over 6. And this angle right here would be pi over 3, and this one right here would be pi over 2. Okay? So I went to a website called Incompetech, and you can design your own polar graph paper there, which is kind of cool. I'll show you how to do it in just a sec. It's really easy. It's a weird name. I got to write them. Why do you call yourselves that? Because they do have an awesome graph paper site. You can design almost any kind of graph paper you can imagine on their site, and it outputs a PDF for you. So to measure something in polar notation means you have to identify the radius of where it is and the angle from the positive x-axis. And the points are always stated r theta. And I usually put a semicolon in between to indicate this is not an xy point. It's a polar point. So this point right here I've just identified as the point 8 semicolon pi over 6. You have a very pink pen today. All right. Okay, so now I could identify this point in rectangular coordinates too, couldn't I? Yeah, because we know that if I turn this into a right triangle, I can use sine and cosine and tangent to play around here. So for example, the x value here that's the y value, oops. The y value here is going to be equal to 8 times the sine of pi over 6, right? And then the x value should be what? Yeah, 8 cosine. Right? And that comes from, in general, we know that, for example, the cosine of an angle is equal to the adjacent side x over the hypotenuse r. And we're just solving that for x. I'm just writing it in terms of x. I got a cough drop here. What's that? It's Fisherman's Friends cough drops. They're very strong. It's like the Chinese mustard of cough drops. Makes your eyes water if you're not used to it. I love them, but they're a little, it's an acquired taste. No, it doesn't, but Chinese mustard, do you know how it like makes your eyes water if you have too much of it? Clears out your sinus, that's what this does too. It makes Halls seem tame. It's got cayenne pepper in it and lots of eucalyptus, and try one if you want. You want one? But they're like, I like them like mints. Yeah, I eat them like candy. Who wants to try one? Okay. My kids usually can handle half or a quarter and then they spit it out. My kids are younger than you guys. You got one there. Anybody else want to dare to try one? I think they taste great. Oh, want to give one to Zach there? They're not expensive. It's like a Hall's cough drop. There's not really medicine. It's got cayenne pepper, eucalyptus, a few other fun things. Okay, let's get back to polar here. So anyway, let's see. So as far as xy coordinates, this would be the point where x is 4, square root of 3 over 2 times 8 would be 4 square root of 3. And 1/2 of 8 would be 4. So that's the corresponding point in rectangular coordinates. So we could easily move back and forth between rectangular and polar. Okay. Suppose I gave you a rectangular point, a different one. If I take 8 cosine of pi over 6, that gives me 4 square root of 3. And 8 sine of pi over 6 gives me 1/2 of 8, which is 4. Okay. All right, so let's suppose I give you a point in rectangular and I want to make it polar. So rectangular, let's take the point 2, 3, for example. I want to change that into polar, r semicolon theta. What relationships do we know between x and y, r, and theta? Well, we've got one of them here. We also know, right, sine of theta is equal to y over r. What's another famous trig function that would be helpful? Tangent, yeah. We know that the tangent of theta equals y over x. And don't we know y and x here? Yeah, so arctangent would tell us theta. So in this case here, theta would be the arctangent. Oops, crazy pen. No, I don't. I don't dislike Vicks, but I just don't use it. I like Fisherman's Friend. It's like, yeah, it is like a, yeah. Arctangent of, in this case, 3 over 2. And the other connection to connect, I want to know what r is. Does anybody know a connection between r, x, and y?
Well, couldn't you solve for y and solve for x?
There's a simpler way. R, x, and y are related in one very famous equation.
R squared.
Ah, there you go. Yeah, Pythagorean theorem, r squared equals x squared plus y squared. So for us here, then, r is going to be the square root of 2 squared plus 3 squared. So we can figure out where the point 2, 3 is by changing it to polar using the arctangent and the Pythagorean theorem. Okay. Oh. So r equals the square root of x squared plus y squared. Had enough? Feel free to throw it out. All right. So I want to remind you we need to be working in radians in calculus. So make sure your calculator's in radian mode. I know. Physics generally does things in... Put it out your nose, huh? Yeah. Excellent. Oops. Oh, come on. Oh, mode. There we go. Okay. So let's see. I am in radian mode. That's good. So I'm going to go to my home screen. And I want to know what is the arctangent of 3/2. Where's divide? There we go. Now, one problem is, what? Oh, I did the tangent. Oops. I meant to do the arctangent. And that number was not what it was supposed to be. That's better. All right. So what that means is a little less than 1 radian. Anybody get a good feel for radians besides the special ones like pi/2 and pi/3 and so pi/3, since pi is bigger, is a little more than 1. Yeah. Yeah, so this is less than pi/3 because pi/3 would be just over 1. So I can kind of approximate where this is. And then my radius is going to be the square root of 4 and 9, which is the square root of 13. So it's about 3.6. So then I can estimate here that this new point, let's do it in red maybe. No, I guess we'll stick with black. Come on. R is about 3.6 and theta is about, was it 0.98? Like right? Yep. Oops, wrong class, that one. 0.98. So let's see. 3.6. 1, 2, 3, 4. So I think this point is right about there. With me? What's the matter? You okay? Did I lose you? No. Okay. So the point of polar coordinates, however, is not to bounce back and forth between polar and rectangular. The real reason I'm going to do it is some problems are easier in polar than they are in Cartesian coordinates, which is the x and y stuff. And so there are some things we can do in polar that we cannot do in the Cartesian coordinate system and vice versa. So it's just a new coordinate system that's necessary for some kinds of problems. So you do need to know the following. If you want to convert something from polar to Cartesian, which is the x and y stuff, and I did not spell that right, well, that means we're taking something like r theta, and we want to change it into something x and y. Then here we have that x is equal to r cosine theta, and y is equal to r sine theta. So that's for converting points. If you want to convert from Cartesian, I think that looks better, to polar, that means you're taking something that started with x and y's and you want to turn it into r's and thetas. So then you have that r is the square root of x squared plus y squared, and theta will be related to, but not necessarily equal to, the arctangent of y over x. Now, why did I say that there? Why might theta not exactly be equal to the arctangent of y over x? Anybody remember that from trigonometry? Why there's a slight problem here? Well, there's multiple. I mean, you can keep going around and get multiple angles. Well, yeah, you got to be in the right quadrant. Anybody remember what quadrants arctangent works in? Almost.
First and second.
Nope.
First and second.
First and fourth. Yeah, it works in the first and fourth quadrant. Arctangent in the circle only works, and it's not just first and fourth, but it only works between negative pi over 2 and pi over 2. So if your point happens to live in a different quadrant, like 2 or 3, you have to translate the angle that you were given. Okay, so I'll give you an example of that, just to be clear. Suppose we have the point negative 2, 3. So that point lives right here, true? I need to identify here what is r and what is theta. R is pretty straightforward. It's going to be the square root of -2 squared, which is 4, plus 3 squared, which is 9, square root of 13, which we already know is about 3.6 from our previous problem. However, when we go to theta and we ask for the arctangent of 3 over -2, what do we get? Whip out those calculators. 3 over -2, yeah, should give us -0.98, which is just less than 1 radian heading clockwise from the positive x-axis. That puts us in the wrong quadrant. Well, the good thing there, where did that put us? Well, it put us right here, -0.98 radians. That's the right slope, it's just the wrong direction. So what can I do to fix that? No, the absolute value of that will put me right there. 180, but what's 180 in radians? Pi. I should add pi to this, yeah. So add pi to this, and then we'll have the right answer. All right. So if we add pi to that, we'll be here. Adding pi puts us right there. Oops. So I'm going to add pi to that. And that will put me in the right spot. Okay. I could have taken pi away from it too. If I took pi away, that just heads at it in a different direction. All right. So I could either say my answer is negative, that -9.8 plus pi, or I could say it's -9.8 minus pi. And that gives me another problem we're going to have to deal with in polar coordinates. Let's see, where's my calculator? So I could either say it's this plus pi. Where's pi? There we are. Or it's that minus pi. So I could call the angle about 2.16, or I could call it -4.12-ish. They both put me in the same spot, the same direction. And the radius says where in that direction we live. So here's another problem with polar coordinates with that in mind. Oops. I could either say this point is approximately, because I had to round my angle, let's see, where did I go? R is the square root of 13. I can do that exactly, but as far as the angle, I can't do that exactly without using the arctangent notation. What did we get again? 2.16, -4.12. Oops, wrong button. So 2.16 about, again, radians, or same point, square root of 13, and then 4.12 negative. So both of those polar coordinates refer to the same exact point. So one problem in polar coordinates is any polar point can be represented in infinitely many ways. Yeah, well, it gives us some really cool possibilities, but it also gives us some problems that we have to contend with. So for example, earlier I looked at the point 8, was it pi over 6? That's the same point as 8, and then add 2 pi to that, which gives us 13 pi over 6. I could subtract 2 pi from that, because 2 pi is 1 revolution, and that's going to give me 11, let's see. Negative 11 pi over 6. Oops, that didn't come out right. You get what I'm saying? Okay. Now I got another weird one for you. You ready? I want you to try and plot the following point for me. Let's let the angle be 7 pi over 6, and the radius be -8. what does a negative radius mean? Go backwards. Yeah. So let me take a screenshot of this and we can try it. Oops. Escape. Okay, so first I got to find 7 pi over 6. So I'm trying to find negative 8, 7 pi over 6. So first I have to find 7 pi over 6. So there's 1 pi over 6, 2, 3, 4, 5, 6. Here is 7 pi over 6, right? Right there. If it was positive 8, then I would head out this direction. But it's negative 8, so from the origin, which is also called the pole, I need to head out that direction. So there's my point. This right here is my 7 pi over 6, right? If it was a positive 8, I would head out from the origin this way. But it's a negative 8, so from the origin I head out that way. So this right here is the point, negative 8, 7 pi over 6. All right, so now we're going to attempt to graph some stuff besides points. We're going to graph a function. And we're going to try it by hand first. Yes. Do you have a question about this? No? I can pause. Anything with polar into my house? Sort of. I made a spiral in the wall. It was. There's a lot of work getting it done. It took a while. It took us like 4 years. It was a long time. I'm almost done. I didn't teach for a few summers, so I was just all my labor. I did most of the work. Some of the supplies were expensive, some weren't. I did a lot of stucco, and I mixed my own stucco, which made it like, I don't know, 1/6 the normal price instead of buying bagged pre-mixed stucco. It was. Okay, can I? All right, well, we're going to get to practice this again, so this is going to get fun. Okay, here we go. Let's see, I need a new page. I need another shot of this guy. We are going to attempt to graph. So usually in polar, you write r is a function of theta. And so what we're going to do is we're going to let r equal cosine theta and see what that looks like. Okay. Now, this gets kind of weird because what's my independent variable here? Theta is my independent variable. So I usually like to put that in the left column and r in the right. However, when we write points, points are always written r first and then theta second. So it's different than the way we write x and y stuff, and we just got to be careful. All right, so we get to practice this again here. If theta equals 0, what is r? No, what's cosine of 0? 1. Don't start plotting points yet. We're just going to calculate table values, and then we'll figure out how to plot them. If theta equals pi over 6, what's the cosine of pi over 6? No. Square root of 3 over 2. Yeah. Which is approximately 0.86. All right. At pi over 4, my next special value, what's cosine of pi over 4? Yeah, square root of 2 over 2, or 1 over the square root of 2, which uses less ink. Wait, hang on, it's approximately 0.71. Yeah, at pi over 3, I get 1/2. And at pi over 2, I get 0. Let's do a few more points. What's the next special angle? 2 pi over 3. It is negative 1/2. So here's 2 pi over 3, and then we have 3 pi over 4, and then we have 5 pi over 6. So let's see. What's next? Oh, 3 pi over 4. Yeah, it's negative square root of 2 over 2. Yeah, 5 pi over 6. Negative square root of 3 over 2, and I'm out of room. Our next point will be pi negative 1. So now we're going to try and plot these points. Okay, so yeah, that's a square root of 3 over 2. Negative. All right, so we got to decide on a scale here, and let's see. How many circles do I have? 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I'm going to make, the biggest number I have here is 1, right? So I'm going to make this outer circle radius 1. So that means the fourth circle, 1, 2, 3, 4, will be radius 1/2. Okay, so 0, 1 is my first point. I'm going to plot that in red. That's going to be right here. Pi over 6, 0.86. So now I got to figure out where the heck that is. So let's see. Pi over 6 is this line right there. And let's see, that is, oh, maybe 8 wasn't a good idea. Oh well. 4/8, 5/8, 6/8. What's, anybody calculate what's 6/8 equal to as a decimal? Oh, that's 0.75. Yeah, what's 7/8? Yeah. 0.82-ish? 0.87. Okay, that's pretty close to what I want to be here. So just inside there is where my next point is. And then pi over 4 is this line right there. And there I want to be at about 0.71-ish. So let's see, this second line in is 0.75. So I want to be just inside that, like maybe right there. And then this line right here is pi over 3. And I want to be at 1/2, which is 4 circles out, which is exactly right there. What the hell is this going to be? And then let's see, at pi over 2, I'm at 0. Interesting. You know, I'm just kind of curious, just for fun. In between right here, that's going to be pi over 12. What's the cosine of pi over 12? Somebody on a calculator? 0.965. So that is going to be right about here, I think. What'd you get? So 0.96? 0.9 what? I don't know. It's close enough for my accuracy with this pen on this board. All right, so we're just kind of curious about that. All right, let's see. We got to keep going. We've graphed all those points right there. 2 pi over 3 is that line right there. What does it mean to have a radius of negative 1/2? So it means I'm on this line right here, but I need to go back through the origin. The origin, by the way, in polar coordinates is referred to as the pole. The pole. So we need to go back through the pole 1/2. So that's going to put me right here. Hey, check it out. That is directly below my point for pi over 3. Those are symmetric. Oh my gosh, are we making a circle here? Let's see, 3 pi over 4 is this line. Yo, Michael, what's up? Oh shit. What is it?
That was here on Wednesday.
Yeah.
Said the same thing that they forgot to give it to you on Monday.
Uh-oh.
Yeah, it's in here. So you're gonna have a hard time.
I really want to know how they come up with the name.
Should you guys plot the rest of those points? Keep going. All of them? Oh yeah, plot all. Oh, okay, I need that. Thank you.
Literally, like, there was probably 6 others
Yeah.
there in class, and all of them said
I
that.
forgot to turn it in. Shit.
So unless you're grading on a curve, it's gonna be really bad grade.
Yeah, I don't want that. We'll figure something out. Let's see.
Later.
See you, Michael. Yeah. Okay.
Anything special?
Yes, section 7.4.
Are you recording it?
Yes. Okay.
No! Oh my gosh, you're doing another yellow line? It's okay, I can handle it.
Oops.
Oh, there's another yellow line. I should
Jesus,
draw that
Jeff,
one.
your line isn't
Oh, you're
cut.
drawing another one.
Oops, except I missed.
Thanks. Ah!
Put that in the wrong spot.
Go get it. Go. Go. Liar.
Okay, here's my points. This middle one got covered up. What does it look like we might have graphed? So like, I'm going to measure something here. What is the distance between this point right there and this point right here? 1. What is the distance between that point right there and that point right there?
I bet it's 1.
And then this point right here and this point right here?
That's 1 too.
Yeah, and this here and this here?
I bet that's 1.
Yeah. So what do you think we just graphed here?
Circular.
We just graphed a circle.
That's fun.
R equals the cosine of theta makes a circle of radius. No. Radius 1 over 2, 1/2. Yes, the diameter is 1. Okay, let's see if we can prove that by trying to translate this into polar coordinates. I mean, rectangular coordinates. Isn't that awesome? Oh, we should graph it on the calculator to see too. Okay, whip out your calculator, put it in polar mode instead of parametric.
Polar. Done. Looks like a seashell more than a circle.
So,
Okay.
cosine of theta. Now, according to the calculator, it treats polar like parametric. In that when you go to the window, you have to give it x, y, and theta parameters. So for x, for theta, I'm going to go from 0 to 2 pi.
Okay.
I'm going to step by 0.01 is probably a little too, I think I'm just going to go by 0.1. For x, let's see, I can kind of look at this and guess, like 0 to 1, that's really all I need to see. I'm going to go a little bit farther than that. I'm going to go from -1 to 2, give myself a little room. And then I'm going to go from negative, I guess I could go from -2 to 2 for y. And graph. And it doesn't look circular here. Ooh.
If we square it, will it?
Yeah. If you do zoom square, it'll look better.
Yeah, that's much more circular.
Oh gosh, mine looks kind of crappy. But maybe I should zoom in on it. Let's go window. Oh.
Or polar. Yeah. Oh, polar, not That's cool. I have a circle. Nice.
Yeah, it takes, whoa, look at that one. Ooh, now check this out. Well, let me circularize it. Oh, mine looks funky. All right, watch this. I'm going from 0 to 2 pi, but how many times did this get traced? Nope. I'll show you again. Let's go 6.3 maybe. Ready, watch. There's 1. There's 2. I went from 0 to 2 pi and it traced it twice. Now in rectangular coordinates, the period of the cosine is 2 pi. But on this polar graph, what does the period appear to be? Pi, yeah, we graphed from 0 to pi and it made the full circle, and then we kept going and they just graphed the same circle again. It's kind of cool. So some polar functions are periodic, but the periods are kind of tricky to figure out. Okay, it twists everything we thought we knew about trigonometry. So I'm going to prove this is actually a circle instead of just saying it looks circular. So we've got r equals the cosine of theta, and what we want to do is we get rid of r and theta and replace them with x's and y's. And here's what I think we need to do that. I think we're going to use the fact that r is equals the square root of x squared plus y squared, and then cosine is equal to x over r, but r is that square root. So rewriting my black equation, the left side r is really the square root of x squared plus y squared. And on the other side, I can replace the cosine with x over the square root of x squared plus y squared. Not done yet. I would like that denominator to be gone, so I'll multiply both sides by the square root. Okay, sorry. So I want to multiply this square root up to the other side. What happens when you multiply square root by itself? It cancels. Now technically you get the absolute value, but the absolute value of the sum of two squares is still positive, so we're okay. So that's going to be x squared plus y squared equals x. Now that doesn't yet look like the equation of a circle to me, right? So I'm just going to, on the next page, circles in rectangular usually look like this. X minus h, where h is the central x value, of plus y minus k, where k is the central y value, equals the radius squared. So we're going to see if we can get it to look like that. We are currently at this point, x squared plus y squared equals x. The black or the blue? Remind you of something? Formula for a circle? Yeah, that came up in Math 95. Yeah, that's the formula for a circle. So I'm going to subtract this x to the left and put the x's together. So x squared minus x plus y squared now equals 0. Anybody remember the trick to make something like this look like that? It's called completing the square. Are you going to say that?
Yes.
Okay.
I remember this. It's been so long.
Okay, so we're going to complete the square. To complete the square, you have to identify the coefficient of the x to the first power term. That's a -1. So you take your -1 and you cut it in half. Then you take your -1/2 and you square it. That gives you 1/4. 1/4 is the magic number we have to add here. Since I added on the left, I better add it on the right too. Now, completing the square means what I've now created is a perfect square with the x's. That's going to be the square of x minus 1/2. Right? Negative 1/2 plus negative 1/2 would be negative 1 in the middle. Negative 1/2 times negative 1/2 gives me the positive 1/4 on the edge. Okay, we're getting there. Now we still have that plus y squared hanging out, which is totally fine. And now on the other side, we have a 1/4. So now here's what I know. I know in this case that my h is 1/2 and my k is 0. And the 1/4 is my r squared, which implies that r must be 1/2. So what we've discovered is that the polar function r equals cosine of theta is a circle with center 1/2 0 and radius 1/2. Is that what it looked like we graphed? Did we graph a circle that has a center 1/2 0 and a radius of 1/2? I'm pretty sure that's what we graphed. Pretty cool, huh? Okay, so I mentioned that we might work on sections 3, 4, and 5. We have only worked on sections 3 and 4. We're not going to get to 5 today. But I just want to show you something really cute on your calculator. So here's my graph of the cosine of theta. What I want you to do is I want you to replace theta with 2 theta and see what happens. Is that necessary? So we're going to go in here. Jeff, focus. We're going to replace theta with 2 theta and graph it. Now I'm graphing from 0 to 2 pi-ish.
That was fun. I like it. Ooh.
Isn't that cool?
Oh, it made a flower.
Okay. Now, I don't know about you, but the resolution on the calculator just makes me sad, as cool as that flower is. So what I've done is on our course website, I put a program for GeoGebra to graph these for you. So let's see. Under the course home, GeoGebra Polar Plotter. So if you follow this link here, come on. GeoGebra has a place called GeoGebra Tube. It's like YouTube for GeoGebra stuff. So I posted a file there that you guys can play with.
Hey, how do you work with GeoGebra? Because I can't get any flowers now. It does not like me.
-4.
Can't figure it out.
You can't figure out how to play with GeoGebra? It takes some getting used to. Now here's one problem with GeoGebra. Polar stuff is wicked hard.
I can't get it to graph though. It's just like it enters an equation, but it'll say graph and it won't graph.
Yeah, so here I put 3 in there, and then I have this slider here
Three is not fun.
so that you can watch it trace.
Oh, that's cool. Yeah.
Oh, that is cool.
Even once it doubles it.
Yeah, odd ones it doesn't. Yeah, so if I put a 4 here, then I'll get 8 leaves.
Interesting.
And then I can keep
Four was pretty cool.
Try 6. That was better.
6.
Six is just a little crazy.
6 is going to give 12 leaves.
Ooh, that's
It's all
still.
pointed at the end.
So would 11 give 11?
11 would give exactly 11 leaves, yeah.
Oh.
Or 9 would give 9 leaves.
Yeah. All right.
Yeah.
I need to zoom in on this.
Now here's what's kind of cool. Watch this. Here's another cute one. What if I did, instead of a whole number, what if I did something like 3 halves?
We're in the same window. From 0 to 2.
Oops, and I need more.
2.5.
But look what happens with, I guess I need to do a different one. Let's do 2/3. I think that'll work out better. Oh, that's not enough. Damn it.
6/5.
6/5. I don't know if my program will graph that. I got to fix my program. I can't do that one. Another program that's good for doing these is called Desmos. Desmos with an S.
How many is that? It's just wow. It's crazy. That's actually really cool looking. I really like
Desmos's motto is beautiful free math. And they have a calculator that's pretty nice. So if I go to Desmos and I type something like R equals the cosine, or actually I'm going to do sine this time, the sine of, and I could do like 3, and then I need to get theta. Where's theta?
well, yeah, it's just that made me give you a birthday present. I should make her brownies. I know she loves brownies.
Darn it.
Well, that was really sweet of you, and it's a great pick-me-up because now I have to go to try not to fail a physics class.
Do you have physics? Ah, there it is.
Right? Physics is so hard, dude.
What second are you guys doing?
We're learning about light and lenses.
All right, come here, let me show you this.
Which isn't actually
Pay attention for a sec.
hard stuff. It's actually not
Paisley,
hard.
Paisley, look. Okay. This is a calculator called Desmos. And Desmos, you can just type R stuff with theta, and it will do a great graph of it. Now, to do that, though, I'll do a new one here. You have to start it off with R equals. If you do stuff with X and Y, it's going to assume rectangular. And then maybe you want to do the cosine. To get theta, you have to hit this more button, and then you'll get theta. And so then you can do stuff with theta. So I could put a 2 out front here, make it bigger. I could do stuff like divide theta by 3 and see what happens. Okay. So it does a pretty easy job graphing with polar. Calculator does an easy job graphing polar. GeoGebra without my little plugin kind of thing does not. And it looks like my plugin needs some work. So polar's fun. We're going to do lots of flowers. Next class I'll show you a polar butterfly. And we're going to make a butterfly.
Can you make it like really pretty with a I'm happy with just a butterfly.
It's you'll see. And then we'll try to do some calculus with polar. Like how the heck do you do areas with polar? It's quite a bit different than rectangular. But it's something we need to calculate.
But I'm just going on
All right, that's it.